a little bit more of potassium handling first, before we get into the renin-angiotensin-aldosterone system, yet again, and then we'll get into our acid-base balance. All right, so far we've talked about what happens in the inner medulla in terms of the movement of salts and urea to create this gradient. What's the purpose of that gradient? The concentrate urine. Okay, it's a specialized part of your loop of Henle, especially your juxtamedullary nephrons, because they're the ones that have the loop of Henle that goes all the way down to the inner medulla. Now, what about your cortical nephrons? They go to the outer medulla. So are they going to be specifically involved in the creation of this steep gradient? Not so much, okay? Your juxtamedullary nephrons are the ones that are going to be involved in really creating this gradient. But all of your urine is going to be able to be concentrated because remember, your cortical and your juxtamedullary nephrons both dump into your collecting ducts. So whatever's produced, whatever tubular fluid is produced from cortical nephrons and juxtamedullary nephrons are going to all enter in. So if this is your juxtamedullary nephron and you have a cortical nephron up here, they're both going to dump into the same collecting duct. So the collecting duct is going to be subject to contact and influence of that gradient generated by the juxtamedullary nephrons. Now, potassium is something that is going to have a role in that as well. It's going to be able to accumulate. It actually becomes trapped inside the medullary region because of the way that it's processed by the nephron. So when potassium is filtered, it's really filtered because it's an ion, it's small enough, it will be filtered through the proximal convoluted and late proximal tubule, the straight tubule. From there, we're going to talk specifically about how it moves, but what really happens is you get reabsorption happening in the very proximal parts. There are a couple different triggers for why that happens. But once you get down into the thin descending limb of the loop of Henle, what you start to see is secretion of potassium into the thin descending limb. So you get reabsorption happening in the proximal tubule, and once you get into the medullary region, depending on the gradients and depending on the concentrations, we're going to end up with secretion happening into the thin descending limb, reabsorption that happens majorly in the thick ascending limb. And then again, we have some more reabsorption that will happen from the medullary collecting duct. What is the manner in which you have potassium being reabsorbed in the thick ascending limb? Sodium, potassium, 2-chloride cotransporter. Okay, so that is one of the main ways that you get potassium being reabsorbed in that thick ascending limb. When we get to the outer and inner medullary collecting ducts, we're going to see that we have, once again, our principal cells, we have our alpha intercalated cells, and our beta intercalated cells, okay? But because of the way that this is cycled, having a lot of reabsorption of potassium in the thick ascending limb, you can get, to a lesser extent, some more reabsorption in the medullary collecting duct, or you can have a greater degree of reabsorption depending on the degree of secretion that happens up here in that distal part. So the excretion of potassium could be anywhere from 10 to 15% if you have a lot of secretion in those distal segments, or it could be about 1 to 3% of your filtered load if you're reabsorbing. And that's something that usually happens if you have reabsorption all along the nephron. What does that mean about your dietary intake? It's pretty low, okay? So for the paracellular side, for the proximal tubular side, it's mainly going to be paracellular. Now, the part I want to point out here is one of the main reasons would be solvent drag. It'll follow along with water being actively and intensely reabsorbed in the proximal tubule. But don't forget that we do also have a change in the luminal voltage. Okay, so even though potassium will follow paracellularly because of water movement, by the time you get to the late proximal tubule heading into the loop of Henle, we've gone from a negative luminal voltage compared to interstitial space to a positive luminal voltage. So you will have some potassium that is just moving on its own away from the repulsive force of that positive luminal charge. Okay, but in either case, we have paracellular movement of potassium to get all the way across that cell. You do have channels that reside inside the cell, but they're mostly for maintaining overall balance, maintaining overall order, and recycling to fuel some of these co-transporters and channels. On your thick ascending limb, we have both paracellular and transcellular. We've already talked about the transcellular side, so that channel, never forget that channel. It does a lot of heavy lifting in the TAL, and it's something that comes up a lot when we talk about the effect of diuretics and how you can modulate the activity of that cell in order to change the uptake of various ions. But we also have paracellular movement, which will happen not only for potassium, but also for sodium. Why is that occurring? Because of the voltage, right? So we still have that positive luminal voltage, which will tend to draw the cations paracellularly through those tight junctions. Okay? All right. Now, we have a couple of different scenarios in the late distal cortical collecting tubules when we're talking about our intercalated cells, especially when we get into that latter portion. This one is showing reabsorption. So it's important to note that for reabsorption, we're looking at alpha intercalated cells. Okay, we also have beta intercalated cells. For our principal and intercalated cells, about 70% of the cells that are in this region are principal cells. That's why they're called principal cells. They're the principal type that is present here. So they're going to do the crux of the work. But they are going to be involved in secretion of potassium. Okay? The beta intercalated cells are going to also be involved in secretion of potassium. Your alpha intercalated cells are the ones that help with reabsorption. This is the opposite effect that we talked about when we discussed chloride. The principal cells and the beta intercalated cells both reabsorbed chloride, and the alpha intercalated cells were responsible for secretion of chloride. So remember when we discussed the appearance and the location of the channels in your alpha and beta intercalated cells? What was unique about that? That we haven't really talked about elsewhere in the course. They're effectively mirror images of each other, right? So because of that, they can have they'll have opposing effects on their role in moving ions, okay? And because they express different channels to make that movement happen, it's possible to have a tighter control over whether we want to reabsorb or secrete a particular ion. And the activity of that particular that particular cell's channels and pumps can be upregulated specifically due to whatever the need is for the body. So when we're looking at reabsorption, how does it get across the membrane on the luminal side? We have our HK pump. So some of these HK pumps, for those of you that did 503, we talked about your proton potassium pump residing in the gastric mucosa. This is the main job for getting acid secretion into the sun. Okay, so your HCl, this is where your H comes into play. They're a class of channel that is related to your sodium-potassium pump. So because of the slight difference in the amino acid sequence and the moieties and the way that it's folded, different pharmacological effects will result in inhibition of your NAK pump versus your HK pump. What blocks your sodium-potassium pump? What's the big one that we always talk about? A lot in 503. Your sodium-potassium pump. It doesn't begin with an O. Lobbying. Okay. Lobbying blocks that, right? Omeprazole blocks the gastric HK pump, but it has not limited effect on the HK pump in the renal system. It can have a little bit of an effect, but not all HK pumps have the exact same, the same moieties, the same binding sites. So it's important to understand that just because you have an NAK pump and you have an HK pump doesn't mean that you're going to have the same activity in every single tissue. So that's not something that I'm going to ask you about if you take omeprazole and how that's going to affect your renal unit. This is not a pharmacology class. I'm letting you know that so that you're familiar with that when it does come up in the future, because inevitably it will. But in this case, we're looking at taking up potassium in exchange for protons. So we're acidifying the urine, the tubular fluid, before it becomes urine, in exchange for potassium. So your alpha intercalated cells are sometimes referred to as your acid-secreting intercalated cells, because your beta intercalated cells secrete bicarbs, so they would be your bicarb-secreting intercalated cells. On the basolateral side, we're looking at the same NAK pump and also some potassium channels that help with just recycling to make sure that sodium-potassium pump is continually fueled. All right, this figure actually came from a paper, but I like it because it included a lot more detail and it showed all three of them side by side. So on the top, we're looking at our principal cell. Our principal cell is going to do what for potassium? Secretion. Okay, so we are taking potassium up on the basolateral side, and we're doing that by the sodium-potassium pump. And then we have these ROMK channels that are going to allow it to be secreted into the lumen. There are epithelial sodium channels that are also residing in the lumen that helps with the sodium being taken up. So sodium will be reabsorbed at this point, but potassium can be secreted when you get to that distal sections of the nephron. This AIC, that's your alpha intercalated cell. And actually, let's see if I can highlight both of these. Compared to your beta intercalated cell, they don't show all of the same channels, but it shows the crux of what was talked about in this paper. And you'll notice that we have our ability to acidify the tubular fluid, because remember the tubular fluid is on the left, on your alpha intercalated cells. So looking here, this is the one that is responsible for acidifying and allowing for potassium to move in transcellularly, and then it will be removed on the other side into the blood. For our beta intercalated cells, everything is kind of reversed, but do you remember when I said that your beta intercalated cells are also called your bicarb secreting cells? Bicarb is going to be secreted in exchange for chloride being reabsorbed. So that channel is involved in the reabsorption of our chloride. Remember, our principal cell and our beta intercalated cell will reabsorb chloride, but the intercalated ones are really going to come up big in our acid-base content. So the principal cells do a lot of the work for our movement of ions. Your intercalated cells kind of aid in that, but also have a big role in acid and base concentrations that show up inside of the tubular fluid. This one came from another paper. I just wanted to show side by side, specifically looking at the movement of potassium. What's happening with potassium if you have a low intake or a normal to high intake, and what is happening along the nephron itself, which is just showing the same thing that we had seen before, and it compares the low and high in a single figure. And then on the right, it's showing the main players in your principal cell and your intercalated cells. Which intercalated cell is this one? Yeah. Right, because we're looking at, we're looking at our potassium that is being reabsorbed into the blood. And because it's being reabsorbed into the blood, it's the one cell that has this role in the distal portion. Is that a little neater? In the distal portion of the nephron. So your beta cell would have a similar effect to your principal cell. All right, so how are we going to control whether or not you get potassium being secreted? One of the things is that you have an increase in your extracellular concentration. That's going to upregulate the channels that are involved, specifically looking at your HK pump. And aldosterone is going to help increase that because of its activity on which pump? Sodium potassium, right? If aldosterone is going to rev up your sodium potassium pump, that means that more potassium is being taken up from the blood, from the interstitial fluid, and because it's being taken up in the cell, it's going to be secreted into the nephron to be excreted from the body. Sodium or volume delivery. This is what we're talking about with the macula densa. That's one of the other effects that is if you have an increased sodium load, then you will increase that potassium secretion as well, typically because you have a higher volume that needs to be removed from the body. Your acid-base balance, your acidosis will decrease the potassium secretion, which we'll see in just a little bit, and your alkalosis is going to increase it. Why do you think you have a relationship between acid and your potassium? The HK, right? They're going to move in opposite directions. If you have, let's go back here. If you have a lot of, acid inside of the blood, okay, so your blood's over here. If you have a lot of acid inside the blood, what are you going to do? What are the kidneys going to do to try to alleviate that acidosis from the body? It's going to try to secrete it into the tubular fluid so that it can be excreted from the body to try and bring the pH of the blood back up to normal values. So if you're revving up the activity of this pump, what happens to potassium? You have more of it being reabsorbed. Okay, so if you have more of it being reabsorbed, you have less of it being secreted. Okay, it's sort of ebbs and flows depending on what the needs are of the body. But that HK pump is the main reason why there's a relationship between acidosis and hyperkalemia. All right, so this flowchart, it just explains everything that we had talked about before, specifically with regard to aldosterone. Aldosterone is going to specifically increase in the cortical collecting tubule so that you get more potassium being excreted. But what's happening at the same time? Sodium is being reabsorbed, so is chloride, and so is water. All right, so how are we going to trigger aldosterone? We're going to regulate our effective circulating volume by a few different methods. We have this is what we're mostly going to talk. This is what we're going to talk about right now. But we have already discussed the effects that we have of ADH, the sympathetic system, and the inhibition of increasing your effective circulating volume by AMP, right? If you release AMP, you're going to excrete more fluid. So you only want to do that if you have volume loading. Under volume depletion, the three on the left in the center are the ones that we're really going to trigger. So since we've already discussed a little bit about ADH or arginine vasopressin and the sympathetic system, I'm going to focus on the RAS, but that also means that ADH is going to come up again in just a second. So, renin-angiotensin-aldosterone system. Your renin is produced as prorenin. It can be cleaved into active renin and released by your juxtaglomerular cells. That apparatus is present where in the relative sections of the nephron? Right around the glomerulus, right where the afferent and efferent arterioles are opposed to that glomerular capillary bed. Renin functions as an enzyme. Angiotensinogen, which is the zymogen for your angiotensin 1, is going to be released from the body by what organ? Anybody know? Liver. It's going to be released by the liver, okay? So, angiotensinogen is released by the liver. It's present, circulating in the blood, but it won't become active into angiotensin 1 unless renin has been stimulated to be released. Okay, so that's why renin would be kind of the trigger. The substrate's there, but the enzyme's not. So when renin is triggered to be released, because of a drop in volume, and therefore a drop in blood pressure, it can cleave angiotensinogen into angiotensin 1. Okay? Angiotensin 1 gets converted into angiotensin 2 by ACE, angiotensin converting enzyme. Where is that released from? Lungs. The endothelial cells in the lungs. It's also released from endothelial cells in the kidney and in other organs, but it's unusually highly concentrated in endothelial cells in the lungs. Okay? So most of the ACE that's floating around your body is coming from those endothelial cells. Angiotensin 2 has numerous effects on the body, several of which we've already talked about, but we're going to talk a little bit about them again. One of which is going to release aldosterone from your adrenal gland. Aldosterone, as we talked about before, is going to trigger the reabsorption of sodium and therefore water. So this one comes from the Boron book, and it kind of runs through the whole flow chart. So if we have up here on the top right, we have a drop in the effective circulating volume. What's one thing that's going to happen first? It's going to stimulate the juxtaglomerular apparatus to release renin. Renin is going to come over and it's going to cleave your angiotensinogen into angiotensin 1. That angiotensinogen is just floating around the body, having been released from the liver. It can't be activated until renin gets that signal. Okay? From that point on, we have ACE coming primarily from the lungs that will cleave 1 into 2. And then angiotensin 2 has a number of different effects. The effect that we've already discussed ad nauseum is the secretion of aldosterone from the zona glomerulosa of your adrenal gland. Okay? So for those of you that had endocrinology, you have those three main parts of the cortical region, glomerulosa, fascicula, and reticulus, that are going to release your aldosterone, your cortisol, and your androgens. Okay? And then inside the medulla, you have your epinephrines and your norepinephrines that are going to be released from the medullary part of your adrenal gland. So just for context, in case some of you have taken endocrinology. Aldosterone's activity is going to come back and act on the kidneys, on the nephron itself, and it's going to promote an increase in sodium reabsorption and water reabsorption, so you have less showing up in the urine. Angiotensin 2 also has a direct effect on the kidneys. What effect is that?
Increased resistance of the efferent arterial.
It's going to increase the resistance of efferent arterial, which increases your GFR. It also slows down your renal plasma flow. It also directly promotes sodium reabsorption by stimulating the activity of the sodium proton exchangers. NHE3 is the one that specifically has phosphorylation sites for it to be able to be activated, and it actually has a couple of different, PKA and PKC have opposite effects. I'm not going to ask you to remember that, but just for your edification, if you are reading and are curious, PKC will tend to inhibit, PKA will stimulate. And so the NHE3 is the one that is particularly stimulated by your angiotensin 2. But when you rev that up, you get more sodium being reabsorbed and also in exchange for protons, which means more acidification of the urine. So when would you see that also being triggered under pH differences? Acidosis or alkalosis? Acidosis, because you're trying to secrete and get rid of more protons. All right, so angiotensin 2, we've talked about aldosterone, we've talked about its activity here. It also directly acts on receptors. It has receptors in the hypothalamus. There are angiotensin 2 type 1 and type 2 receptors, your AT receptors, in the hypothalamus that function as osmoreceptors that can stimulate thirst, because the whole point of this is to increase your effective circulating volume. So you want to take more in. It also stimulates the release of vasopressin, or antidiuretic hormone. So angiotensin 2 has a direct effect on the kidneys. It has an effect on the adrenal glands. It has an effect on the vasculature, right, to cause vasoconstriction. It also has a direct effect on the receptors in the brain that promote the release of something to increase water uptake from the kidneys and also promote the increase of taking in fluids from the outside. So it stimulates your thirst. Okay? Angiotensin 2 does a lot of stuff. How do we feel about the RAS system? Pretty good? I know there's a lot of moving parts, but hopefully, since we've kind of touched upon it in almost every single lecture, hopefully this should be a little bit more like a summary. And This just is to list the examples that we talked about, the smooth muscle cells for vasoconstriction, mainly in the efferent arteriole, but also in the body. It still is going to act on other arterioles in the body. It's just that in the kidney specifically, it has a bigger effect on the efferent side. That's why we specify that. The effect on the kidney is upregulation of the channels to promote sodium reabsorption, the hypothalamus and the pituitary gland, the hypothalamus for your thirst signal, the pituitary for release of ADH, and the adrenal gland for the release of aldosterone. So this was a recapitulation from before. It's the same figure that I can remind you of it again just for context. It came up previously in the lecture material. This shows a little bit more of the medullary region and the effect on epinephrine on the same type of cell, and the zona glomerulosa in the cortical region that is the result of the release of aldosterone, as well as your insulin that all can function to increase the activity of your sodium potassium pump. But since I've already asked you that a few times, it sounds like everybody's pretty much got the aldosterone increases NAK pump activity down pat. So, all right, last part about summarizing our potassium movement. These figures are from the Bohren book, and it shows the difference between our alpha intercalated cell for our reabsorption in exchange for secretion of protons. So this is our acid secreting cell. The alpha intercalated cell promotes the reabsorption of potassium in the distal segments of the nephron. And your principal cell, which makes up 70% of all of the cells in the distal section, is going to promote the secretion. So you're really going to ramp up the activity of the principal cell function in order to get rid of all that extra potassium that most of us are taking in our dietary daily routine. All right, this is, I think, the last slide. It's a summary one that I found from a different book. I can't remember what textbook it was right now, but this one is, at least shows the same thing that we talked about before, but I think from the Bohren book, the way that it's written out, the arrows sometimes might be a little bit more difficult to follow. This one is a little bit more clear to show specifically the effects. Sympathetic activity is the same kind of sympathetic activity. It's going to increase your sympathetic activity, but the effect of vasoconstriction is going to be the same thing that your sympathetic system does. So this will summarize where each site is located. Remember we said that there's some that comes from the kidney, but most of it comes from the lungs for your ACE. The liver produces angiotensinogen, your JGA are going to produce the renin. So this whole cascade is really important in the overall function of helping to regulate your volume. The reabsorption here, it's important to understand specifically that it's going to trigger the increase in reabsorption of your sodium, and because it's triggering sodium reabsorption, it's also going to trigger chloride reabsorption as well, and it's doing so in exchange for the potassium secretion, so you get water coming in. The effect is retention of salt and water to make sure that your blood volume goes back up and your blood pressure goes back up and you don't pass out. How are we doing? I see a lot of just blank statements, so do we have a question before we go on to ask this? Alright, so you have questions, we're going on. Alright, this is technically our last official lecture. There are not very many slides in here, so it will actually be pretty quick, but by the time we get to the end, we're going to run through looking at lab values so that you'll be able to look at specific lab values and tell me, is it acidosis or alkalosis? Is it respiratory or metabolic or both as the cause? And is it compensated or not? So the first thing we want to do is talk a little bit about the specific concentrations that we see and the pHs that you would see in different parts of the body. Your arterial blood is typically around 7.4. That's your physiological pH, and we usually are talking about your arterial blood when we're discussing any type of values here. But I will give you the venous values as well for context and comparison. You don't need to memorize the concentrations, but it would be a good idea to know the 7.4, which you should know by now. You're going to need to know the barriers beyond which your arterial blood will be considered acidic or considered alkaline. And it's good to know that the inside of your cells is typically more acidic because of the production of all of those organic acids in response to metabolism, cellular respiration. The urine can be anywhere from an acidic pH to a little bit above your arterial one. When would you see a more alkaline pH show up? We talked about one example at the end of respiratory.
High altitude.
High altitude, and people at high altitude tend to have an increase in ventilation rate, which means what for their pH of their blood? It's going to be higher. So what is some medication or, I guess, blocker that they tend to take to try and excrete extra bicarb? Acetazolamide. Okay, we're going to talk about acetazolamide again. But acetazolamide will promote the excretion of bicarb from the kidney. So it's one of those things that people who are going up to high altitudes to climb might take to try and stave off that pH change due to the low oxygen tension of the air. So you can produce alkaline urine based on the needs of the body. Gastric hydrochloric acid, that's just there for comparison to show you just how low your pH can drop in the stomach. All right, so your normal pH, we're looking at 7.4. Anything in your arterial circulation that is less than 7.35, that is acidemia. It's not technically acidosis, because acidosis would refer to the tissues, the extracellular interstitial fluid. Acidemia is acid pH in the blood. So anything that causes either acid to accumulate or bases to be lost, either one of those is going to affect the pH and cause it to drop. For alkalosis, we're looking at anything that is above a 7.45. So it's a relatively narrow margin between the two. And again, this is going to be something where if you lose too much acid or you gain too much base, it can cause the pH of your arterial blood to go above that value. We have three different lines of defense that we're going to talk about specifically. The acid-base buffering system, which is your biggest one that we've talked about a lot. Bicarb. Okay? Bicarb is a big buffering system in your body to control pH. We do have a few others that are going to show up in the kidneys. The respiratory system, we already covered that. What happens if you have a lot of an increase in the partial pressure of CO2 in the body? pH goes up or down? Down. Right? Lots of CO2, lots of protons, low pH. Okay? So the respiratory system is not quite as fast at buffering the extra acid or the base as your bicarb is in the circulatory system, but it is the next quickest way to get rid of extra acid. The kidneys are going to be the more long-term and the more potent actors in regulating the pH of the body. So if we're looking specifically at bicarb, our bicarb, we have this same pathway that we talked about a lot. This is looking at how it acts inside of your own blood cell. This should be very familiar from the respiratory unit. What is Ca? Carbonic anhydrase. Okay, your carbonic anhydrase is going to catalyze that reaction to form carbonic acid. To be perfectly honest, not every single carbonic anhydrase makes the carbonic acid intermediate. Sometimes it kind of cuts out the middleman. All right, so it is possible to do that. And the reason I say that is because we have a lot of different carbonic anhydrases. So far we've talked about it as if it was just sort of one enzyme. It's actually a family of enzymes, and acetazolamide only acts on one of those family members. So carbonic anhydrases all have the same function, but the type that resides in each different cell is going to have a slightly different isoform. So carbonic anhydrase 1 is the one that you find in red blood cells. That's the one we've been talking a lot about. Carbonic anhydrases 2 and 4 are going to come up to, and a little bit of 12 when we start talking about what's going on in the kidney itself. But bicarb is one of the most important buffers in your extracellular fluid to allow for the buffering of any extra acids that happen to come into play. Chemistry. You guys remember what the equation is on the top? The bottom is just showing you the concentration of CO2, since we're looking at the concentration of a gas in a liquid. I just rewrote it on the bottom specifically for Henry's law, right? What is alpha for Henry's law? Say again? Oh, not the number, but yes, you're right, but not the actual number. What does it represent? So you're going to multiply that by the partial pressure. Do you guys remember the figure from Henry's law? We had two beakers, and it showed the partial pressure on the top, and then it showed the concentration that was inside. And we talked about if you increase the partial pressure of the gas above a particular liquid, you'll get more of that gas being dissolved. But you have to take into account how soluble that particular gas is in that particular liquid. Okay, we're talking about a very specific interface. So your alpha is just the solubility. Okay, so the bottom equation is just taking into account the solubility of CO2 in your blood in this example. All right, so how is a low pH of your plasma going to affect ventilation? This should be a little bit of review from the last unit. So lots of protons, what's going to happen to your ventilation? Why? To try and do what? Bring down your CO2 partial pressure by blowing it off. So all of those elevated protons are going to stimulate mainly your medullary central chemoreceptors in order to trigger an increase in ventilation so that the partial pressure can go down. That's one way that you can reduce the overall amount of protons that's circulating around the body. Okay, it's a respiratory way to reduce the proton concentration and therefore bring the pH back up toward physiological range. What about high? So high pH, alkaline. Right? If you already have a relatively alkaline pH, what you really want to do is bring your PCO2 back up to try and lower it back down to normal. This is what happens when people have panic attacks and they tell you to breathe into a paper bag. Right? You're hyperventilating, and that's causing the pH actually in your blood to go up, and some people can actually lose consciousness because of the high oxygen in the body as well. And so telling you to breathe into a paper bag is really just having you rebreathe your own expired air. So it forces you to elevate the carbon dioxide partial pressure in your body, which reduces the concentration of, reduces your pH to bring it back down to normal. Has anybody ever had that or seen anybody do that where you have to breathe into a bag? That's the mechanism by which that would happen. Because the effect would be to try and reduce the protons, bring the protons back up so that you can have a reduced pH. So the relationship between your alveolar ventilation and the pH of your arterial blood is that the higher the pH, the lower the ventilation. That's your compensatory mechanism to try and counteract the effect of an alkaline pH or alkalemia. How do we feel so far? I know we haven't actually gotten to the kidney's job yet. But that's going to come. So, first let's look at respiratory changes. Under conditions of acidosis, we have anything that is going to trigger above that 45, okay? Now, this 45 is the sort of the upper limit for, oh, it didn't show up. Alright, well, maybe it'll show up in a minute. The upper limit of your acidosis in arterial blood. Okay, the upper limit for venous blood is actually going to be 51. So while the partial pressure is going to hover somewhere between 35 millimeters of mercury to 45 millimeters of mercury in the arterial, we're actually looking at, well, it'll show up when I assign it even if it's not showing up now. So on the venous, it's going to be 41 to, oh, that looks awful, 51. Okay. Oh, it is, there we go. Just didn't show my G. Okay, so specifically, this is for PCO2. Okay. The values themselves are things that you really ought to know, okay, especially the arterial ones. Most of the time, we're going to be looking at arterial blood gases, so 35 and 45 is what you really ought to know. But it is important to understand that the acceptable range in your venous blood is going to be a little bit higher. Why? Metabolism. You just picked up a whole bunch, right? You picked up a bunch. Some of it's going to be carbamino compounds, some of it's going to be existing as bicarb, but you're going to have more of it existing as partial pressure in, there we go, the venous side. So what is typically the partial pressure of carbon dioxide in your venous blood? 45, 46. 46 is probably a pretty good number because it's halfway between 41 and 51. What about on the arterial side? 40, which is halfway between 35 and 45. So basically, if you could remember the numbers that you typically found for partial pressure of carbon dioxide in arterial versus venous blood, plus or minus 5 in either direction gives you the range of what is considered technically within the normal, acceptable partial pressures, okay, for each blood type. So, things that can cause that acidosis or alkalosis condition. Acidosis, we've talked about this a lot. If you don't have adequate alveolar ventilation, you are not breathing sufficiently rapidly, and because of that, you'll have CO2 accumulate in the body. You can get that from CNS problems, so it can also be from a PNS problem. So one of the CNS problems would be like poliomyelitis. It's something that can affect the central nerves, and that can affect your respiration rate. PNS example would be Guillain-Barré syndrome. That's something that will affect the peripheral nervous system. Lung or chest wall defects, we talked about that a lot when we discussed our restrictive diseases. You can also have a condition where you're producing too much CO2 for what your body's ventilation rate is doing. So you're probably going to increase your ventilation rate, but it's still not able to overcome the amount of CO2 being produced. We talk about malignant hyperthermia a little bit when we get into skeletal and smooth muscle in 503, specifically because of the mutation that triggers that when exposed to certain types of anesthetics. And what it does is basically it ramps up metabolism. So malignant hyperthermia, your skeletal muscles are really respiring at a very high rate, so they're producing a lot more CO2 than the respiratory system is usually equipped to handle. The other part that could cause acidosis from a respiratory issue is if you're just breathing in more CO2, which hopefully you're not, but if you're in an environment where the CO2 actually is palpable inside the air, then that could happen. For alkalosis, any kind of head injury, stroke, those are things that can promote an increase in your ventilation rate depending on what nerves are affected. Pain or fear, stimulation of the sympathetic system, ramps up that ventilation rate. Hyperventilation due to peripheral chemoreceptor stimulation, or you could have pulmonary causes that are going to cause you to increase your ventilation rate in an attempt to get more oxygen. The end result is you get alkalosis if you do that too long without any kind of controlled feedback mechanism to slow it down. All right, metabolic changes. So for metabolic changes, we're looking at our 21 to 25 for, 22 to 26, or 19 to 25 is the Venus, sorry about that. We're looking at our arterial circulation again. Acidosis would be under conditions where your concentration of bicarb is anything less in the arterial blood of 22 milliequivalents per liter. So for Venus, I'll write that up here again, it's 19 to 25. Anything that goes above that concentration of 26 milliequivalents per liter means that you have alkalosis. All right, so this specifically is a metabolic problem. Your respiratory problem is acid or base because of changes to carbon dioxide partial pressure or concentration in the blood. For bicarb, that concentration can fluctuate as well, and it can cause acidosis or alkalosis depending on the degree to which that change occurs. If you have acidosis, these are some examples of what can cause that. Carbonic anhydrase inhibitors, diarrhea would be the loss of intestinal bicarbonate. That assumes that will persist, assuming that you are still able to eat, and therefore that diarrhea is able to continue because the secretions that are coming in the GI tract are not only very potassium rich, but they're also rich in bicarb. So chronic diarrhea would result in a loss of intestinal bicarbonate and can cause acidosis as a result, assuming that you're still eating. Severe diabetic ketoacidosis, I mean, it's right there in the name. That will also be something that will be the result of too much acid to be able to be buffered and accounted for with your bicarb. Because bicarb is a base, when it drops below a certain point, you're considered acidotic. For alkalosis, vomiting is a really good example of it, mainly because you're losing that really, really low pH, a lot of protons from your gastric acid secretions. So if you are vomiting, anytime you eat anything, you're still going to produce that acid. Anytime, technically, you smell anything or see any food, your stomach already starts to produce acid. So any kind of vomiting, even if you haven't been able to keep anything down, could still be the loss of acid, okay? So vomiting is something that will cause alkalosis. Obviously, if you eat a lot of antacids, you're basically chewing on a lot of bicarb, so you're going to rev up the amount. That would be something that is under conditions where maybe you have peptic ulcers, right? Or you have a lot of acid reflux. Chronic use of antacids to try and control that pain means that it's not very well managed, and that can cause your blood pH to go up. Diuretic or laxative abuse is something else that we discussed actually in the previous one that has to do with the upregulation of the channels involved in the normal function of moving acids and bases, which we're going to talk about in a second, because what is the pH of your urine usually? Not the number, just relative. It's acidic, okay? It's more acidic. And every time you secrete a proton, you're basically producing a bicarb that's going to be either reclaimed or it's going to be a new bicarb that's being reabsorbed in the body, okay? So if you are producing a lot of urine, you get a loss of acid as well as the production of new bicarb, so you're actually increasing your base and losing your acid at the same time. So taking too much of that can result in alkalosis as well. So how do we compensate for this? On the top, we're looking at our values. So at the top, we're looking at our values of acidosis and alkalosis in which part of the body? Which type of blood? This is arterial, right? What would the pH values, well, the pH values are really the part that we're going to be measuring your arterial blood, but specifically the values for your CO2 and your bicarb are going to change based on what is tolerable in arterial versus venous blood. But on the top, we have under conditions of acidosis, under conditions of alkalosis. This one's saying, what is, if the problem What is the problem? And then what would be something that would compensate for it? So if we're looking at either too much acid or too little acid for acidosis or alkalosis, the problem is the CO2 levels. Okay, so the problem is the respiratory system. The respiratory unit is not doing its job to be able to regulate the level of CO2. It's not properly regulating that. As a result, you have a pH change in the blood. So one of the big ways to compensate for that is the kidneys. Okay, if the respiratory unit is, your respiratory system is not capable of handling that CO2 levels and responding to shift it back in a way that will restore it to physiological pH, the kidneys will kick in to compensate for that. If you have acidosis because you don't have enough base, or you have alkalosis because you have too much base, this is a problem with the levels of bicarb in the body. All right, so if the problem is a bicarb problem, it's considered a metabolic problem. So that would be your metabolic acidosis or your metabolic alkalosis. Compensation, the fastest way would be the respiratory system. Okay, if you are acidotic, stimulate an increase in ventilation, you blow off some of that extra CO2 that helps to compensate for the fact that you have very little base. The kidneys are your longer term adaptation. The reason for that is because it involves the upregulation of certain channels, which involves transcription factors, which involves transcription, processing, translation, insertion into the membrane, and then function. So it takes a little bit of time. All right, so now we're actually going to get into what kidneys do. We have three main ways that the renal system is going to control the overall pH of your blood. We are either going to secrete protons and reabsorb any bicarb that was filtered in the tubular fluid, so that bicarb will be taken up and reabsorbed directly into the interstitial fluid, or we're going to produce new bicarbonate. So the kidneys actually do a really good job of making more bicarb. Bicarb is not something that typically should be a major component of the urine. Mostly what we see in the kidneys is if it's acid, it's got to go. If it's bicarb, it's got to stay. And we even will make more bicarb because of the amount of acid that is constantly being produced. Where is the acid coming from? In every cell in your body? Cellular metabolism. That respiration just produces organic acids as a byproduct. Lactic acid is a good example under anaerobic conditions. So in the early segments of the nephron, what do we see? We have our acid over here on the tubular lumen side. Where is that acid coming from? It's coming from the conversion of CO2 and water from both the interstitial fluid and the tubular lumen, just diffusing into the cell and being converted by carbonic anhydrase in order to produce a proton and a bicarb. Okay? So a bicarb is going to be reabsorbed across into the interstitial space, and the proton is going to be secreted in exchange for sodium. So that's the sodium proton exchanger that I had mentioned before, the NHE3, that will be phosphorylated to upregulate the reabsorption of sodium in response to angiotensin II. It also promotes the secretion of more protons. The protons can then be recycled to continue secreting more protons, but most likely you're going to be producing so many protons because some of that CO2 substrate and water substrate are coming in from the interstitial space. So all of the protons that are leaving through the luminal side are doing so in the early parts of the nephron, your proximal tubules and your thin descending limbs from your sodium proton exchanger. And on the basolateral side, we're looking at our sodium bicarb co-transporter to move that bicarb into the interstitial space. So this is a new production of bicarb that's showing up in the kidneys. In the more distal segments, we no longer have sodium coupled with that proton movement. So it's just ATP hydrolysis to secrete that extra amount of proton. Chloride is going to follow so that it's electrically neutral, but that proton doesn't need sodium reabsorption to occur. Why? We don't really have a whole lot of sodium left in the tubular fluid by the time you get to the distal segments. So if we relied on sodium to secrete protons, we wouldn't be able to acidify the urine as much. So instead, we just use ATP and just pump out as much of the proton as we can. Why do we need ATP? What's the typical pH inside of the cell compared to the outside? It's 4-7. Right, so it's not going to want to move. It's not going to voluntarily move. All right. This one shows the same things that we were talking about before, and I'm going to zoom in on this one, mainly because I put this all in one slide. This is from the boron book, so that I can show you the different types of carbonic anhydrases. The next slide will show it in a little bit more depth, but in the early part of the proximal tubule, we have two carbonic anhydrases. We have one that is a GPI link, so glycophosphatidylinoxetol moiety linked to the membrane on the luminal side. That GPI linked carbonic anhydrase 4 is the one that's blocked by acetylcholine. Okay? It has a much higher activity on CA4 than it does on CA2. CA2, which is a soluble form, resides inside all of the cells along the nephron. But CA4, and to a lesser degree that 14, reside on the membrane itself. Okay, so acetazolamide mainly acts, or only acts really, in the proximal tubule. It has a much lower efficacy when you're binding to carbonic anhydrase 2. For that reason, it's stopping the conversion of bicarb into carbon dioxide and water. And if it's stopping the conversion so that it can go into the cell and basically reconstitute that bicarb so it can be reabsorbed, you are stuck with that bicarb in the lumen. That's where the bicarb comes from. When you block that CA4, you are using acetazolamide to stop bicarb from being converted into a form that can cross the membrane and have it to allow it to be transcellularly moved into the interstitial space. So that bicarb can't be reclaimed, which means it stays inside the tubular fluid. Yeah. So what we're looking at here is we have our carbonic anhydrase 4 that is present in contact with the lumen tubular fluid. Bicarb on the top left there normally is going to be converted into carbon dioxide and then also water. Those two can diffuse across the membrane into the cell. The carbonic anhydrase 2 will take that CO2 and that water and make a new bicarb that can then be moved across the basolateral membrane in conjunction with sodium. So sodium and bicarb will move across the basolateral membrane into the interstitial space. That's one of your reclaimed bicarbs, but technically it's a new one because you broke bicarb apart and you formed a new bicarb. Okay, it's not actually reabsorption of bicarb. I'll get to that in just a little bit. But if you had acetazolamide, which blocks that carbonic anhydrase 4, the initial conversion no longer takes place, and bicarb itself can't get into the cell in that proximal tubule. If it can't get into the cell, then it stays in the lumen, and it contributes to the basic part of the pH of the lumen. So you can have a more basic pH in your urine if you force bicarb to stay in the tubular fluid. It also causes water to be retained. But it does so because it's this guy that's blocked by acetazolamide, which isn't showing up, but it'll show up when I assign it. You also have other carbonic anhydrases that are over here on the basolateral side that can help do the same thing if you want to be able to recycle. Okay, this one is also carbonic anhydrase 4. So it resides on both membranes. But if we're specifically looking at the ability to reabsorb the stuff that's already been filtered, locking it on, there we go, locking it on the apical side means that bicarb stays inside the fluid. Now, you'll notice that the carbonic anhydrase 2, carbonic anhydrase 2 is found also in the late straight proximal tubule, it's found in the thick ascending limb, it's also found in your alpha intercalated cells in your medullary collecting ducts. So the part that I want to point out specifically for our proton movement is that we have sodium proton, sodium proton, sodium proton in the early parts. And then we have the proton pump. So our sodium proton exchanger, all the way through the thick ascending limb. But then once you get to the latter portions, you don't have a lot of sodium floating around, so you have either in exchange for potassium, which we talked about at the end of the last formal lecture file, and also this proton pump. So different mechanisms to get secretion, but all levels of your nephron are secreting acid. Your body has a chronic problem of just producing acid. So the kidneys do a really good job of making sure that all acid gets removed from the body to maintain pH levels inside the blood. How are we doing? All right. So, acid secretion everywhere, coupled with sodium in the beginning, coupled with potassium, or just straight ATP hydrolysis for that H pump when you get to the distal sections. The second mechanism is your bicarb reabsorption. Bicarb is going to be reabsorbed along all segments of the nephron. It's done by these conversion of carbonic anhydrases. Remember this one? We talked about this as your proximal tubule. Okay? Your proximal tubule is going to have the GPI linked in the membrane and also have the soluble form. Okay? So this proton leaving is going to do so by what mechanism? What's the mechanism of the proximal sections for secretion of protons? Okay, that says sodium, or it will say sodium eventually, in exchange for sodium, okay? Remember that in the beginning, any protons being secreted in a lumen is in exchange for sodium through that NHE, sodium proton exchanger. Your carbonic anhydrases, there are several different types. So this one actually came from this paper that really studied just activity in all of these different types of carbonic anhydrases. Carbonic anhydrase 2 and 4 have very high activities, especially in the kidneys themselves, and acetazolamide has a stronger activity on carbonic anhydrase 4 than it does on carbonic anhydrase 2. So if you wanted to inhibit the reabsorption of bicarb, you can get a more alkaline urine because it's stuck. This is the way that it gets inside of the cell. Now, we also can form new bicarb. So from here, we are looking at the production of acids and the production of ammonia that's going to happen all in different places along the nephron. So we're going to talk about the formation of new bicarb, but we're also going to talk about the relationship that has to ammonia and ammonium. This is going to be really important for overall processing by your liver. The formation of new bicarb is really what happens when you're just taking the carbonic anhydrase that is inside of your cell and collecting any CO2 and any water that's being produced in response to normal cellular metabolism. That CA2, that carbonic anhydrase 2, still has activity, even if there's no breakdown of the bicarb coming from the lumen, like we saw in the proximal tubule. The bicarb from the lumen results in a bicarb showing up in the interstitial space, right? It's not technically the same one, but it's considered reabsorption of bicarb. In this case, we're not collecting bicarb from the tubular fluid. It's just the production of new bicarb that results from normal function of that soluble carbonic anhydrase. This will happen everywhere along the nephron, all of your cells. But when you produce new bicarb that goes into the interstitial space, you're also producing a new proton that is going to be secreted into the tubular fluid. How do we make sure that that proton stays put? Especially when we get to the areas where the voltage in the lumen is more positive, we occupy it with a buffer. So phosphate functions as a really good buffer. The divalent phosphate will interact with protons that are constantly being secreted into the lumen to form that monovalent phosphate down here at the bottom. That monovalent phosphate is not going to be able to go inside the cell. And because it can't cross inside the cell, it sort of traps that acid in the tubular fluid. Okay? Now, this one is from so the previous slide was from the Boren book, this one's from Guyton and Hall. So it is a little annoying that they keep switching. They have different orientations. But in this case, the tubular fluid is on the right and the interstitial fluid is on the left. But I wanted to show you this specific one because it's not always just, it will bind also with sodium. Sodium will have a role in forming this buffering system. So the previous slide really just showed it as HPO4 and H2PO4, whereas it will also interact with any sodium that's present in the proximal parts of the tubule. Okay, and we know that we're in the proximal parts of the tubule because of which channel? That sodium proton exchanger. That's how we know we're in the early parts of the nephron, because of the expression of that particular channel. So, ammonia buffering, this is actually going to be really important. This comes from the Guyton and Hall book, but we're going to zoom in on this leftmost side to show you what is happening. How do we get ammonia being produced inside of the nephron? It happens in the proximal tubular cells because of glutamine. Glutamine's coming into the cells and it's actually being converted and producing ammonia in the process. In the collecting tubules, we're going to talk about why we want to make sure that our ammonia is going to be able to be secreted into the tubular lumen. So first off, our ammonium excretion, the first principle I want to talk about here is that your protons can move, but your ammonia can cross over that membrane. And when ammonia crosses the membrane pretty easily, if it interacts with those protons, you form ammonium. That's a charged ion that stays. Ammonia is toxic to your body. You do not want it in your blood. Okay? So in this case, the process of normal cellular metabolism produces ammonium. That will split into an H plus and an NH3, both of which can cross the apical membrane, and reconstitute that ammonium NH4 plus ion and allow it to be trapped inside the tubular lumen. The process of that also produces a new bicarb. So anytime carbonic anhydrase is employed, we're making more protons to secrete, we're making more bicarb to reabsorb. This is the mechanism for producing those ammonium ions. So when glutamine comes in, you can convert that with the production of an ammonium ion to glutamate, and then the dehydrogenase makes alpha-ketoglutarate, producing another ammonium ion, and then the end production allows for gluconeogenesis. So the whole purpose of this is metabolizing glutamine to get more glucose. All right, but the process involves the production of ammonium. Ammonium is something that we want to get rid of in the body. So it will cross into the tubular fluid of the proximal tubule, and those ammonia and protons will bind to make that NH4 plus that traps it inside of the tubular fluid. Okay? The descending limb, we have the same principle involved. Okay? But we're not producing ammonia, it's just any ammonia that's coming from the interstitial space. So the kidney's job is also to help make sure that you are not having too much ammonia that resides in the body. It can produce it, but it has a way to get it out, and anything that is coming from the interstitial space also can get trapped inside the renal nephron. Okay? One part that I want to point out, where that little red arrow is the fact that ammonium it's really good at stealing the spot of somebody else. In this case, your ammonium can take the place of this proton in that NHE exchanger. That sodium proton exchanger, it can also be a sodium ammonium exchanger. That's the mechanism by which ammonium directly can get kicked out of the cell. It can also take the place of the proton in that pump. So both of these are ways for ammonium to get out of the cell directly, sorry, on the bottom, by hijacking protons, seat on these channels. Otherwise, it has to separate into your proton and your ammonia. So the main role, I should specify that, the main role is actually this guy down here on the bottom. This channel is really where you're going to get your ammonia coming out. So that sodium proton exchanger can also transport your ammonium. You don't really see that as much with the proton pump. Thick ascending limb, turns out, ammonium is also very selfish and allows it to be able to be taken up by occupying potassium site on the sodium potassium 2-chloride cotransporter. Oops. So in the thick ascending limb, we actually have reabsorption. We are sending it back into the interstitial space. The reason for that is because up here in the more distal segments, we do not want ammonia. If ammonia can easily diffuse out of the cell, and you're in close proximity with the blood vessels, right, for your afferent, afferent arterioles, it's too easy for ammonia to get back up into the blood that has to then be detoxified by the liver. So by having secretion in the initial portions, reabsorption in the thick ascending limb, it allows the ammonia to avoid the areas where it could show up back in the blood. Then it can be secreted again in the distal portions to allow your body to excrete it from your blood. It excretes, again, by taking potassium spot on the sodium potassium pump, and then ending up in the tubular fluid as by being separated into NH3 and H+, and then reconstituting NH4 in the tubular fluid. This is the last slide that just is a summary of everything that we have talked about so far. But I do have a couple of very quick questions. I will assign these also for homework, but I want you guys to take a second so that we can talk through this really quickly. Because this is sort of our last opportunity to talk about it as a group. So let's say you have these values where your pH is 7.12, your arterial CO2 is 50, and your bicarb in the arterial are 18. First of all, is this acidosis or alkalosis? Acidosis, below 7.35. What about the PaCO2? Is that high or low than normal? It's high. So is that contributing to acidosis or not? It would cause acidosis, right? So since the PaCO2 level matches what actually we see as the pH, it's one of the problems. What about your bicarb? Is that high or low? It's low. What does a low bicarb mean for a pH? What would that cause? That would cause acidosis, right? A low bicarb, too little base means acidosis. So this one is which type? Respiratory, metabolic, or both? It's both, okay? Because a high CO2 and a low bicarb both contribute to acidosis, and the pH is acidotic, okay? The last question I had here was 7.15, acidosis or alkalosis? Acidosis. Bicarb is 8, high or low? Low. So is that a problem or a compensation? It's a problem, it's the cause, right? Low bicarb is causing acidosis. What about your PaCO2? Is that high or low? It's low. Is that something that would cause acidosis? No. normally that would cause alkalosis. And because the low PaCO2 normally causes an increase in pH, but our pH is low, that is a compensatory mechanism, okay? So in this case, we're looking at metabolic acidosis with a partial respiratory compensation. Why is it partial? Because you're still acidotic, okay? So you can have partial or complete compensation. But when you're looking at these, I would look at the pH first, then write down what the bicarb level would cause, what the PaCO2 would cause, and see if it matches the pH. That will help you determine if it's one of the causes of the pH imbalance or if it's one of the compensatory mechanisms. Okay? And that's the end. These will be assigned as well. But the